kind of disillusioned with all the word problems with the derivatives. I'm here to tell you we're going to start the new year off easy. But it's not going to last. But we're going to start the year off easy. Who likes finding the area of a rectangle? No, do not be negative about finding the area of a rectangle because that's just ridiculous. Okay. Well, I was trying to get you to say something right, but just I thought I was leading you right to that. No, we love that. We love that. I'm recording. Yep, I heard everyone gets to hear you guys say it. No, that's hard. Rectangle area. That's impossible. It's ridiculous. Yeah. I know. The Scantrons I gave you have 4 options, and yet there are choice E for that optional take home. I'm going to get you new ones, hopefully by tomorrow. Yeah. Oh, if you got E, you're wrong. No, there's definitely. Why would I give you that? All right. Oh. Hi, hi, hi. We're here. Okay. What we're starting today, what we want to do today is approximate the area under a curve. Now, I didn't draw the parabola in. You might want to draw the parabola in. It's y equals x squared plus 1. So you know what that would look like. It'd be y equals x squared moved up 1. And eventually, we're going to be able to get the exact area under the parabola from 0 to 3. But today, we're just going to find the area of each of these 3 rectangles and add them up. Now, do you think that's going to be a little less than the actual area or a little more? The area of these 3 rectangles as opposed to the actual area under the curve from 0 to 3? Now, this parabola keeps going. It's going to be less, right? Because I'm going to be missing these little bits above them, right? Well, I had to make this kind of exaggerated to get the point. So that's it. If you can get the area of a rectangle, you can do this. Okay? So, just to make sure we're all on the same page here, how do you get the area of a rectangle? Length times width. So let's say that the width is this dimension right here. What's the width of our first rectangle? Okay, so it's 1 times, what's the height of our first rectangle? 1, because it's y coordinate right here. All right, so 1 times 1, I'll move this over here. The area of our first rectangle, which happens to be a square, is 1. All right. The next rectangle, what's the width? 1, right? See the difference in the x? Now, the height, how did you know it was 2? Eyeballing it, or do you have a real way? Put what in the equation? What number? Whose y coordinate do you want? Do you want the y coordinate? The height of this rectangle is y when x equals 1. You see that? It's this y, the y coordinate. Every point on this graph, this parabola, the y coordinate equals the x coordinate squared plus 1. So if you want to know what y is here, you take 1 squared plus 1. So that's 2. So what's the area of our second rectangle? 2, right? 1 times 2 is 2. Okay, moving on to the third rectangle. What's the width? 1 again. Now, figure out the height of this rectangle. 5? You guys seeing it's 5? What x value did you plug in? 2, right? You wanted the y coordinate when x is 2, and you're right. 2 squared plus 1 is 5. So the area of our third rectangle is 5. And if we add these together, we get 8. So we know the real area under the parabola from 0 to 3 is greater than 8, but it's an approximation. Any questions on that? All right, let's try the next one. Well, actually, I have to explain a couple things to you. Okay, but don't get worried with that. Okay, what we're doing is we're going to use rectangles to approximate area under the curve, and we call these Riemann sums. And we also are going to use RAM when we're talking about using rectangles to approximate area. Rectangle approximation method. That's what that stands for. And so we'll be approximating area. After we use rectangles to approximate area under curve, we're going to use trapezoids, because those are pretty cool to work with too. So that's what we're going to be doing this week. So I want to just, the thing is, there are different directions that you might be given to get the height. And so I just want to go through each of these. Now, when it comes to the width, you're always going to do the same thing, the width of your rectangle. If I ask you to approximate the area under the curve from x equals 1 to x equals 7, what's the length of that interval from 1 to 7? 6, right? And if I ask you to break that up into 3 intervals, or if I want you to fit 3 rectangles in there, what would the width of each one be? 2, because you took the length of the interval, 7 minus 1, and you divided by the number of rectangles. So that's what I have over here. The width is always going to be b minus a. If the interval is from a to b, you want to get b minus a, that's the length of the interval, and divide it by the number of rectangles, n. So this is what you use to get the width, always, if you're just given an equation. But as far as the height of the rectangle, it depends on the direction, the directions that they give you. They might ask you to use a right-hand Riemann sum or right-hand rectangle approximation method. If they put an extra r out front, that means use the y coordinate on the right for each interval. So like if you break up your interval according to the width, and you're trying to figure out whose y coordinate should I use to be the height of each rectangle, if there's an r there, they say use a right-hand Riemann sum, you're going to use the y coordinate on the right for that rectangle. If they tell you to use a left-hand Riemann sum, or they ask you for LRAM, they mean after you break it up, you know the width of each one, the height is going to be the y coordinate on the left for each subinterval. And by the way, this little sub n here, that tells you the number of rectangles. Whatever that number is, that's how many rectangles I want you to use. If there's an m in front, that's a midpoint Riemann sum. And for that, they want you to use the y coordinate of the midpoint of each subinterval. That's a little trickier. Now, there are 2 other terms that can also be used to describe how to get the height. Inscribed or circumscribed. If you're asked to use inscribed rectangles, they want you for each rectangle to take the smallest y coordinate to be the height of that rectangle. So whatever the lower side is, or wherever the lowest point is, that's the height for that rectangle. So whenever you use inscribed rectangles, it's always going to be an under approximation. If they ask you to use circumscribed rectangles, they want the height to be the greatest y coordinate of all the points for that subinterval. So you'll take the greatest y. So we've got left, right, midpoint, and then inscribed, circumscribed. We'll go with the other 2. Let me show you how easy this is. You're going to love it. Okay, first one, we're going to approximate the area under y equals 2x minus 3. What does that look like if I graph it? Line. Okay. Y-intercept -3, slope 2. There we go. Something like that. We want to approximate the area under this graph from x equals 2 to x equals 5. 2. Now this is just going to be, something we could get the exact area, but I'm just trying to show you this method. The very first thing you have to do is get the width. They're asking us to use 3 subintervals. So think about what's the width of each of the rectangles going to be. If you're going from 2 to 5 and you want to use 3 subintervals, 3 rectangles, yes, 1, right? As for the width, you take b minus a over the number of rectangles, which is 3, and that's equal 1. Okay. Once you figure out the width, now you know the first one, the x's for the first rectangle start at 2, and I'm just going to add the width. So if I add 1 to 2, 3. So I know the x's for my first rectangle go from 2 to 3. How about for my second rectangle? I go from 3 to 4, and for my third rectangle, the x's go from 4 to 5. So every one every rectangle is going to have a width of 1. So when I want to get my, what are we using? Inscribed rectangles. The width is going to be the same for each one. So I could pull it out. I know it's 1. I'm going to fill that in a second. But how many heights should I have if I'm using 3 rectangles? 3, right? So I got to figure out what that first height is, the height of my second, and then the height of my third. So instead of doing width times height plus width times height plus width times height like we did in the do now, if the width's the same for every one, you can just pull it out. And we said that width is 1. So we got to figure out our first height, the height of our first rectangle. For inscribed, let's see, first rectangle, the x's go from 2 to 3. Inscribed means you have to choose the smallest y value to be the height. Okay. Whose y coordinate do we want? 2. So we're going to get f of 2. We'll see what that is in a second. I want to see you to choose 2 because you want it to be the smallest y value. So there's our first rectangle. Whose y coordinate do you want to be the height of the second rectangle? The 3, because you see how the f of 3 is the smallest y? So f of 3 will be the height of the second rectangle. And what about our last rectangle? Whose y coordinate do we want? 4. It's going to be f of 4. Now let's just figure out what these y coordinates are. We have the function is y equals 2x minus 3. So when x is 2, what's y? 1. No, because she just did 2 times 2 minus 3. How about f of 3? 2 times 3 minus 3? 3. How about f of 4? 2 times 4 minus 3 is 5. All right, so what's the sum of the areas of these 3 rectangles? 9. Okay. Now we know the actual area has to be greater than that because inscribed always winds up with an under approximation. Okay, we're also asked in this problem to find the sum of the areas of the circumscribed rectangles. So it's the same picture. I mean, a lot of this stuff is going to be the same now. Just going to draw it over though. So we have 2. The width doesn't change. Doesn't matter what way they're telling you to get the height. The width is still 1. So I know I'm going to break it up at 3 and 4. So 4. Okay. So it's still, you know, the width times the sum of the 3 heights. Now the heights are going to be different because we're going to choose for the heights to be the greatest y coordinate on each subinterval. So for the first rectangle, whose y do we want? Yeah, it'll be f of 3. I have to draw them in as I go. Right? Whose y coordinate is going to be the height of the second rectangle? F of 4. And for the last rectangle, f of 5. Oops. Alrighty. F of 3, we already figured that out last time, right? That was 3. F of 4, we already figured out that was 5. Oh, we never figured out f of 5. 7. What do we get for that? 15, which we know is definitely an over approximation of the area because we got all this extra up there. Well, if we wanted a better approximation, what could we do? Take the average, which actually turns out to be what you would get if you use trapezoids. That's Wednesday's lesson. That's what we're doing in your birthday, Nicole. Doing trapezoidal method. Thought of that for you. Thought you'd like that. Okay, so that then is inscribed, circumscribed. You can see that. Let's try an example using the left, the right, and the midpoint. Are you bored? Okay, that's good. I get it. All right, this is, I'm telling you, this is a nice come back to school kind of easy. What does the graph y equals x squared plus 4 look like? Parabola. What does that plus 4 do to the graph of x squared? Yes, you know. When you have a number added or subtracted outside of the function, it just moves it up or down. Yeah, that's so important. No, I'd rather you tell me. Oh, man. Transformations of functions is probably the most important thing. Wait, I don't like how I did this. I'll move this over. Oh, that's good. So y equals x squared plus 4, just a problem moved up 4. I don't care about that part of it. Because I want to approximate the area under it from 1 to 3. From x equals 1, x equals 3. So 1, 3. And so we want to use, look at this, RAM4. What is that little 4 telling us? 4 rectangles, okay? So, and it doesn't matter whether we're using LRAM4 or RAM4, we're using 4 rectangles, so what do we got to get first for either? The width. What is the width of each rectangle going to be? Yes, you know. 1/2. How'd you get it? 3 minus 1 divided by 4 is 1/2. So now we got to fill in the other endpoints of each of our subintervals. We know the first rectangle, the x is at 1. We're going to go up by the width, which is 1/2. 1.5 or 1.5, which I write? I don't care. 1.5. So this would be 1.5. Then we go up 0.5 again, or 1/2 again. What are we up to? 2. And up 1/2 again, 2.5. Now you got to know what x is we have here, so we know what numbers to plug into the function to get the heights. Okay, so we'll do the RAM4. So we already figured out the width. I'll just write it like that. But we got to figure out how many heights should we have if we have 4 rectangles. What's that? 4, right? Always make sure if they ask you to use 4 rectangles, you only have 4 heights in there. So if you notice, there are 1, 2, 3, 4, 5 numbers here. If you want 4 intervals, you need 5 endpoints. So you're not going to use every single number you see. All right? So the width is 1/2. For the height of the first rectangle, if we're using a right-hand Riemann sum, think of the first rectangle, the x's go from 1 to 1.5. Whose y coordinate do we want? The 1.5. For the first rectangle, it's going to be f of 1.5. The second rectangle, the x's go from 1.5 to 2. Whose y coordinate do we want? 2, f of 2. The next one, f of 2.5. And then the last rectangle, the height will be f of 3. So which x did we not use? And I said we're going to have 5 endpoints for 4 subintervals. Let's see which one we never used of these. The 1, f of 1. Now, you could do this. It's not hard to square these and add 4. I do want to make sure you guys are aware of, on your calculators. Oh, I did the wrong thing. Yeah. If you have your calculator out, one thing, you know, when you have a bunch of heights to calculate, you don't feel like plugging numbers into the function over and over again. You can just enter the function in y1 and set up a table. Now, you'd want at what x do you want to start your table with? You could do 1.5 for this one. Since we're doing the next one, I'm going to start at 1. But for the delta table, what do you think? How much do you want the x's to go up by every time? 0.5, the width, right? So if you go to second window, that's when you set your table up, you always have to tell it where to start. You could always start it for these at A. And this is the big one, though. The delta table, that's how much you want the x's to go up by, make it the width. Because now if you look at your table, all the values you need are going to be sitting there. You just look at them. I'm not saying you have to do this, but it's good to know what, that you can do it. So second table, I have my f of 1.5 is 6.25 and the f of 2 and 2.5, whatever. And so you can fill those in. Any questions on doing that? Oh, did I lose you? No, you're good. Okay. What is it here? Okay, so I don't know why I wrote 1/2 instead of, I should choose decimals or fractions. Make a decision. 0.5. So that was 6.25. Yeah, that's right. F of 2 was 8. F of 2.5 was 10.25. F of 3 squared plus 4 is 13. Ooh, that wasn't a good reaction. Interesting. Okay, now let's see. What do we get when we do all this? We get 37.5? Oh, 18.75, final answer? I like it. I think that's right. Sounds familiar to me. Did anyone get a different answer? No? All right, I'm buying it. All right, that was using a right-hand Riemann sum. Now let's use a left-hand Riemann sum. See the LRAM? That L is just telling you to use a left-hand. It's going to be very, very similar. So we still have 4 rectangles, so we still need the 4 heights. Width doesn't change, right? Width is still that 0.5. But if we're using a left-hand Riemann sum, that first rectangle, the height is the y of which coordinate? For the first rectangle, it's f of 1. It's not f of 1.5 like it was when we did the right-hand side. So it's f of 1. It's the height of the first rectangle. The second rectangle is going to be f of 1.5, right? The third rectangle, the x's go from 2 to 2.5. Whose y do we want? 2, f of 2. And then the last rectangle, f of 2.5. So this time, we didn't use the y coordinate at 3. Right? Now we're doing the left side. We used f of 1, f of 1.5, 2, and 2.5, but we're not using the f of 3. We still have 4 rectangles. We need 4 heights. Okay, let's fill in the values. That's just 1. Was it 1 squared plus 4, right? Yeah. Okay. So we have 5 plus 6.25 plus 8 plus 10.25. And we know we can get something good for that one. 15.25? Anything different? 14.75. Yeah, that sounds familiar to me. Questions where we're getting these numbers from? Okay, so that was the only thing they wanted here. Okay. So this time we got a chance to try the LRAM and the RAM. Ready for another one? Yeah. Please, sir, can I have some more? Now, this time, we are not given the function. They just gave us some points. How many points did they give us? Let me see. Are there 10 or 11 points that they gave? 11, right? So if you have 11 endpoints, how many rectangles can we make? 10. It's always one less than the number of endpoints, the number of subintervals. Now, technically, I could sit here and plot them out. I'm not really going to do it because I don't have that much patience. But we're given the velocity, inches per second as a function of time. All right, they tell us the velocity at certain times. At time 0, the velocity is 0. There's a point. At time 1, the velocity is 12. 0, 3, 4. I'm not going to do them all. Don't worry. I know this would be painful. 8, 9, 10. All right, I should do this. All right, so it goes up. All right, this is really rough. But just so you can see it. 5, 13. By the way, I would never accept this from you if this was your work. 7, 6. And then it goes down here. 2, 6, 5. Okay. I just want you to understand that you're given these 11 points. All right, you're not given the whole curve, just 11 points on the curve, and they want you to approximate the area under the curve. Point just at certain points. So, you know, you give you a table of values, that's it. They gave you these 11 points. And the first thing they want us to do is approximate the area under the curve, which happens to be the distance traveled, using LRAM. These are the easiest problems, table problems. You don't have to figure out the heights. They're sitting there. They're just sitting here. You just got to know which ones to pick. Move this away. Okay. All right, so we'll try the LRAM 10. All right, first of all, what is the width of each one of these rectangles? 1. Do you see that? We're very lucky. These are all evenly spaced. The difference between the times is always 1. That's going to be your width. So I can factor it out. I'm never going to fit them in there. Because I need 10 heights. Now, the first rectangle, the times go from 0 to 1. If I'm using LRAM, whose y, according to what I want to be the height of the first one? 0. And that's going to be 0. Plus the height of the second rectangle. The second rectangle, the times go from 1 to 2. Whose y do I want? 1. If 1 is, yeah, it's going to be all in order. Do you see that? It's going to be plus 12. It's the height of the second one. And then the third one, 22, and you keep going. 22 plus 10 plus 5 plus 13 plus 11 plus 6 plus 2 plus 6 is going to be the height of the very last rectangle, okay? Because when you get to that last rectangle from 9 to 10, you want y on the left side at 9. That's the height of your very last rectangle. So don't just use them all. Don't use them all, kids. There's always going to be one extra one. Know which one not to use. All right, we do that. What do we get? 87? That's true. That is 87. Excellent work. Okay, let's try the R round. 10 rectangles again. We got a width of 1. So that's the same. But the heights. The first rectangle, the x's go from 0 to 1. Whose y do we want for the height of the first rectangle? The 1. So that's 12. So the height of our first rectangle now is going to be 12. And what do? I just keep adding until I get to the 5, right? It's just going to be all some of all these. Want me to show you it in more detail? You get that? While I'm here. 10 plus 7 plus 13 plus 11 plus 6 plus 2 plus 6 plus 5. So it should be. So was it 92? Should be 5 more than that one because the 0 didn't matter. That was 87. This one's 5 more. I like it. Okay. Now comes the fun. MRAM, what does that M stand for? Midpoint. They can't ask you with a table problem to use 10 rectangles. The reason they can't is because if you use the midpoint, you would, like for the first rectangle, if I use 10 rectangles, they all at a width of 1, whose y coordinate would you need to know for the height of the first rectangle? 0.5, and you don't know what f of 0.5 is. You can't just make up numbers. So they can only ask you to use 5 rectangles for the midpoints. So we're going to use the midpoint rectangle approximation method with 5 rectangles. Whoa, that's going to throw off the width. The width is no longer going to be 1. Well, you're still going from 0 to 10, but now you're only fitting 5 rectangles in there, 2. And we're okay with the width now is going to be 2? So the width is going to be 2, but I got to make sure that I have only 5 heights, since I only have 5 rectangles. That's the biggest mistake the kids make. They put too many heights in there. All right, so let's look at the very first rectangle. Let's figure out what its height is. So you said the width of it's 2. So the first rectangle, the x's go from 0 to 2. Whose y coordinate do you need to be the height of the very first rectangle? 1, f of 1, which is, bam, 12. Okay. The second rectangle, the x's go from 2 to 4, so whose y coordinate do you need? 3, f of 3. That's going to be 10. Nice. The height of the third rectangle. Yeah, we're going to need to know f of 5 because the x's go from 4 to 6, midpoint 5. So pop 5 in there, and that gives us 13. Starting to see a little pattern here, right? We had the f of 1, which is 12, and the f of 3, which is 10, and the f of 5, which is 13. What's the height of our fourth rectangle? 6, because it's f of 7, right? And what about the last one? Oh, 6 again. What does this add up to be? I think I know what it is. 74? 94. Yeah, that's what I thought it was. All different answers, depending on how we get the height. What's that? Yeah, any idea how you can make these approximations? Well, with the table, you can't do anything. But if you had just a graph, what could you do with the widths to make it a better approximation? Would you want the widths of your rectangles to be greater or smaller? You want these rectangles to approximate the actual area better. Yeah, if you shrink down those widths, make the limit of the width approach 0, you've got yourself the actual area, which will be an antiderivative that we'll get to next week. If you instead of using like 4 rectangles or 5 rectangles, you use an infinite number of rectangles, so the width of each one is approaching 0, then you're going to get the actual area. Oh, next week. Beginning of next week. I might even touch on Friday. It's kind of exciting. All right, I got one more thing I got to show you before I do my little summary. Sometimes you're given a table of values. So remember, there's no making stuff up with tables. And so this time I've got 4 points. How many rectangles am I going to be able to make? 3, right? So what's different about these problems is that, look at the widths. If I actually, maybe if I drew it a little second here. I got the point 0, 2. There's a point. 3, 7, 5, 4, and 10, 5. So I got these 4 points, right? They're not the same width. And remember before we factored out the width because it was the same? Can't do it. So it's no biggie. We're just going to get the area of each rectangle separately. You just can't factor out the width. We can handle it. Okay, so we agreed we're going to have 3 rectangles. So we just got to figure out, oh, we can't factor out the width. And I just said, oh, don't factor it out. So we're actually just going to do width times height plus width times height plus width times height. We'll just do them separately. Okay, so for the first rectangle, what's the width? 3, right? The x's go from 0 to 3. So it's 3 times, what's the height of the first one? If we're using LRAM. 2, very nice. So 3 times 2, I can even draw it out. So that first rectangle is an area 6. Right? Moving on to rectangle number 2. What's the width? 2, because the x's go from 3 to 5. So that's your width. And the height of my second rectangle, 7. So 2 times 7, that second rectangle has an area of 14. And the last rectangle, what's the width? 5. And the height, 4. So we're not even going to use that last point. So 5 times 4, that's 20. So we have 6 plus 14 plus 20 equals 40. Okay. Let's do a little RRAM here. Oh, I got to do this one really fast. Okay, it's not going to affect the width of each one. The heights are going to be different. So the first one still has a width of 3. But if we're using RRAM, what's the height of my first one? 7. So it's going to be 3 times 7 plus the next one. It's going to be 2 times 4 plus 2 times 4. And then the last rectangle is 5 times 5. So what do we got? We got 21 plus 8 plus 25, 54. Sounds good. All right, let's fill in this little summary. We got it. Okay, so when can we factor out the width? When the width's all the same width. And how do you find the width? What was that little formula? Do you remember when you just have the equation? B minus A over N can't be factored out if they're different. And this occurs usually, they're usually different widths only when you have like a table or they give you the intervals. LRAM will be when f is increasing. If your function's increasing and you use the left side, it's going to be an under approximation. And if your function's decreasing and you use LRAM, it'll be an over approximation. And the number of rectangles is always 1 less than the number of endpoints. This is a fun one, right? It's good. There's 2 sides to the worksheet. I drew the rectangles in on the first side, so you can just actually look at the rectangle. On the second side, you can draw them in yourself.